So Euclid, that's a European space mission that is currently being built by the European Space Agency. It's coming from a long story of concept, starting from the early 2000s. In early 2000, there were in Europe, there were two main groups, one pushing for a cosmic shear machine, so a wide field imager in the visible, and another one who was pushing for a wide field imager in the infrared. And both answered ESA call for mid-class mission. So mid-class mission in this case was 600 million euro, and were in competition. So it was in 2007, and then ESA selected the two and tell them, well, you're going to merge these two concepts and do a machine with wide field imager in the optical, wide field imager plus spectroscopic capability in the infrared. So this has been going on. So then you have this. There was still a competition because there were 4 missions that were still in a competition. And then in 2010, I think Euclid was selected as being the second M-class mission to be launched. The first one M-class mission to be launched is called Solar Orbiter, so that's something to study the sun. And so Euclid was the second one. At the time it was selected, we are speaking about the launch of 2018, and now we are more towards 2020. But while Euclid is interesting for us, and what is the microlensing story linked to Euclid? So you have seen this figure a number of times. At least there is one figure that you could use as a kind of summary why we need to go to space. You take this one. So this is from Bennett Henry 96, microlensing event with a short-lived perturbation here that is due to an Earth mass planet. And here you have different, you see the different amplitudes. It's for the same planet, but for different source stars. So when you have a small source star, you get a big excursion. If you have a big source star, well, the signal is almost flat. So if you want to detect Earth mass planet in the galactic bulge, you have to monitor small source stars. Small stars are faint. So here that's a CTIO image of a microlensing event, and that's an HST image. So you see, obviously, if you want to resolve these small source stars, you basically need high angular resolution. So it's obvious that the next generation of microlensing experiment are high-resolution observations with a wide field and 24 duty cycles to be able to monitor and detect these planets. So, 2002, Dave Bennett and Henry wrote the first paper advocating for space-based microlensing. So the idea was to have a dedicated satellite with a wide field imager to do this kind of measurements. In 2004 and 2005, with Yannick Méliès, we were actually trying something else. There have been some big hope related to Dome C, to Antarctica. Because in 2003, people said that, well, in Antarctica, you could have a 0.3 arcsecond thing if you had 30 meters altitude. So there was a hope to maybe be able to do some cosmic shear and microlensing measurements. So we worked with this with Yannick Méliès, but after all, it was a bad idea. So we never published anything. And then started to look more towards space. In this period of time, Bennett, Gaudy, and others were advocating for space-based microlensing, so we are in the mid-2000s. And then in 2007, there was this cosmic shear proposal that was submitted to ESA, that later came Euclid. At the time, it was Dune. So actually, I had joined Dune at this moment to basically try to have a microlensing program on board. So the idea was to have a 3 months of microlensing program. And the selling speech that I was using is that everything that is good for cosmic shear is good for microlensing, because it's much easier to do. So if the stringent requirements are coming from the cosmic shear, so we can just basically live with the cosmic shear requirements. So well, we published some papers about it. Then when Dune and the space mission merged into Euclid, so we kept with the microlensing program on board Euclid. So it was always put in the legacy science box, because in Europe, if you buy a car to go from, for example, from Pasadena to Santa Barbara, there is no way you could take the car to drive to Los Angeles, to Las Vegas. So you do one science case. So they wanted Euclid to be identified as a cosmology machine. So you put cosmology first, and then you have the legacy box. So microlensing has been in the legacy box ever since. Then, of course, you know that in 2010, you have the decadal survey in the US with W first. And there is one important ingredient for microlensing surveys in space is the thesis of Matthew Penny. Because he started his thesis with Eamon Kerings in Manchester, and it was to basically try to do the proper estimates of the yields of the microlensing surveys. Because what we were doing in the first phase was to use the Bennett-Henry simulations and do a bit of scaling now. So the first time real simulations were done in a clean way was during the thesis of Matthew. It was done first for Euclid, and then, well, basically Matthew joined you here, and is in charge of this for W first. So it also means that all the machinery that you have behind studying the performance of Euclid and W first, that's the same with basically the same guy as a source. So when you hear a Euclid talk, this is normally what you will see. So basically all this top-level science requirement, and as you see, it is really pretty much cosmology-oriented. So dark energy, testing gravity, dark matter, etc. So the goal is with them is to do two kind of survey. So first, a weak lensing survey in the optical, and then a photometric survey in the infrared, complemented by also a survey with a spectroscopy. So here on this slide, you have everything about Euclid. So the launch date, at the time this slide was made, was December 2020. It seems that now we have passed, we will be more towards January 2021. So launched from Kourou, put on the L2 orbit for thermal stability reason. Here you have the small model of the satellite. So here you have the telescope and then the payload module below. There is one thing that is particular to Euclid. It's that you see here there is a shield on the side. Well, the shield is, of course, to protect the sun, so that for your thermal stability, you just want to be always at 90 degrees of the sun with a shield. But because we have no contingency for mass, it means that the shield is somehow short. So it means the debatement angle of the satellite is somehow less than W first, and I will come back to this a bit later. And then you have the two cameras. So the Viz camera, which is so it's a 0.5 square degree camera with optical CCD. So it's a broadband filter, because the main goal of this is to do shape measurements. And then the NISP, where you do near-infrared spectroimaging. So it's also a 0.5 square degree focal plane with 16 CCD. So they are the Hawaii 2K ones. Here, the pixel size is 0.3 arc seconds. So it means in the infrared channel, the pixels are much bigger than what you get for W first. So during all these years, there were, of course, different groups working. So, for example, there is a survey working group to try to define the observing strategy. And what we are working on is with a survey duration of 6 years for the mission, with potentially an extended mission. The V's, these detectors have, when they are in space, they deteriorate with time. So it means the V's focal plane will deteriorate along the mission, whereas the near-infrared detectors only should be living longer. So what they were thinking is that to do a survey of about 6 years, with probably 5.5 years dedicated to two surveys, so a wide-angle survey and a deep survey, and have something like 6 months dedicated to additional science. So this is basically what has been baselined from 2010. The moment when we will decide what will happen to the additional science should be actually a little bit later this year. So after one of the review phase that will take place in October, then the Euclid board will make a call to say, okay, we decide that there should be 6 months of additional survey, and then you have 3 months to write a document and put a bid to finally do it. So you have, of course, there are supernova people who would like to try to get it. And there is also some proposition of a Milky Way survey, where you just monitor part of the plane. Okay. So as you can guess, with this kind of project, so now Euclid has become really an army. So you have about 1,000 scientists being registered, and there are also, of course, some American scientists and people from JPL, with Jason Rohn in particular to lead the charge. Just to give an idea for those who don't know, the amount of data, you speak about 100 petabytes of images. So when you speak about data processing, it is big. And so that's why there is agreements with people from particle physics to use their resources at the Center for Computations for Particle Physics to actually deal with this data. Okay, so that's just a view of this camera. So basically just CCDs with 0.1 arcsecond pixels. So the full width at half max should be, if I remember correctly, 0.18 arcsecond. The NISP is a more complex instrument, and actually both are being built right now. So there are small issues to be sorted out, but things are going more or less okay. So, Euclid Survey, 15,000 square degrees for what is called the wide survey, and 40 square degrees for what is called the deep survey. Oop. And here you have put the limited magnitude for this. So it is really dedicated. So basically you would observe for more or less 1 hour every field and then do all the 15,000 square degrees of skies. And as you see, there is always this legacy box in which we will try to be at some point. So just pass this. Where the field are located, well, if you want to do a deep cosmological survey, you avoid the galactic plane. Makes sense. You avoid the galactic center. So here you have the Euclid wide, that is in pink, and then you have the Euclid deep survey, and this band is the LSST stripe. So just to show you where we are in terms of timeline, you can say that well, the nominal mission should start something like probably 6 months after launch. So you can say late 2021, that's when really the science observation will start. And then there will be a first release of 2,500 square degrees, and then the second one, and then the third one. Okay, I told you something about the shield. The fact that the shielding of Euclid is somehow narrow, so that basically the satellite has to remain at 90 degrees from the sun, plus or minus a small angle variation. For cosmic shear and all this global survey, it doesn't have much importance because you just have to observe at the moment where it is in your field. But for microlensing, it has an importance, and that's why I'm going to show you why. So in practice, Euclid can work from -1 to plus 31 degrees. So you have 32-degree angle. So if you want to observe a field in a galactic bulge, you can observe from here, there, and then 6 months later, this and there. So it means, because of the shield, you cannot do 70 days of microlensing survey like you would for W first, but you can do only 30 days. And then there was a question is that, well, with 30 days, can you still do the science? So there were simulations that were done by Matthew. Well, with 30 days, we can still actually do the science. It is only if you would go really at longer. So if you do, for example, 15 days, that you will really pay the price for it. So the bottom line is that if you want to do Euclid microlensing, you can basically observe for 1 month, twice a year. And because of the low rocket contingency, then you cannot extend the shield. Okay, so I just go quite quickly on this. So this is basically the PhD thesis of Matthew. So he was just trying to take all the up-to-date parameters of the mission and try to define what would be the real optimal survey. And I'm just going straight to the yields, because you have seen the things about W first, so that you just see what are the numbers when you compare with W first. So the strategy would be to observe 3 fields of 0.5 square degree each every 17 minutes in H-band, and to take every 12 hours observations in V's, J, and Y. So at the time, Matthew did some simulations to figure out which was the most efficient way in terms of bandwidths. And the most efficient way is actually to do it in H. In V's, there would not be possible to do it because of the data rate. So we would have a data rate issue when we couldn't download all the images. So the philosophy is 3 fields, so in total 1.5 square degrees, observed every 17 minutes with the color information every 12 hours. The other thing would be to do these mass measurements. You want to be able to constrain the centroid of the source and of the lens. And for this, well, since things are moving by a few milliseconds per year, you just need observations as early as possible in the life of the satellite. So the idea would be to do a mini survey during the commissioning phase, where we would observe the target fields for maybe 24 to 48 hours, just to really take some deep images in all these bands. And this would basically be useful as a reference for astrometry. And this is one bit where this information actually could be used also for W first, because we would have, since it will be probably in 2020, so if you just have a W first launching in 2026, you have 5-year baseline. So the order of magnitude would be to detect something like 35 planets per month, so 5 Earths and 15 Neptunes. If you take the SUMI result for free-floating planet, so we are speaking about 15 free-floating planets per month, so of course this number should have to be reduced. And Euclid basically would complement the parameter space probe by radial velocity and Kepler. So the main focus would be to measure the cold planet mass below 1 Earth mass. So that's what we'll be able to do. So in other words, it is not as powerful as W first, because W first will go further. But here you can basically start to do part of the science case of W first. There would be also a possibility of simultaneous Euclid and W first observations in the extended mission, because normally the infrared detectors should be alive once even one focal plane in the V's will be dead. So could we, for example, try to do parallax between Euclid and W first? Well, it would mean that they are not on the same orbit on L2 next to each other. So for this, that's one of the things we have to study. The first thing is that, well, what would be the final orbits for Euclid and W first? What they will tell us in terms of parallax? And would they be useful in terms of parallax for normal microlensing events? And if there are free-floating planets of low mass, would they be useful for this? So this is something that will have to be studied. So it's a work that has not been done. Okay. So I just pass this because you have seen all of it. Okay, and the last thing is that you can ask is, okay, if Euclid decides to do a microlensing survey, the decision will be probably spring next year. But then when it would take place, because we would ask 4 months, so if they give us 4 months, what we know is the first 3 years of the survey, they are very eager to use the V's camera when it is really operational well, to the best of its ability. So they would consider to do additional survey, probably from year 3 or from half of year 3. So the thing we would be bidding for would be to start a microlens, so to do an early survey with Euclid, so early on in the mission, just basically a few days max of observations. And then from year 3 to do 1 month of observations, and then ask for 1 month a year when we are in the extended mission phase. So this is basically what we have in mind. So for this, the charge was led by Eamon Kerings and me. So we are just waiting, since all the homework has been done and published, well, in particular, thanks to Matthew. So we basically are just waiting for the rules of the game to be written, so that we know, well, okay, now you have to supply a 30 pages document under this form, and then Then we'll build up a team of Europeans for this, and then also we'll see how we are allowed to invite our American colleagues, and then we'll answer to the call to the best of our ability. So it means we are quiet now because basically our homework has been ready, so but we're just waiting to know when we will have the big examination, and then we'll bring everybody on board. Thank you. Yes. Well, since you have heard so many things about microlensing, there was no point in going into the details. Yeah, Jennifer?
So you said it's possible to do 2 months per year. What's the separation between
I think there is 5 months between the two. Do you remember? Yeah. It's not exactly symmetric. It's not exactly symmetric.
So with 5 months, you wouldn't really see the same events?
No. No. No, there will be separate events, yeah.
Question?
I can't remember this. Is it using reaction wheels or thrusters?
It was at the time where the simulations were made, it was, well, you did both. You had reaction wheels and the cold gas. But now, from what I remember, the times are much better now than what you had in your simulation. So probably we would win 2 or 3 minutes, I think. So I think it would be more 15-minute sampling now than, so maybe we'll be able to go to 4 fields. But it is much better than at the time you were on it.
So for parallax solutions, if both go to L2, the maximum separation is of the order of maybe 2 million kilometers at most.
Yeah, if they are like that, but if they are like...
You don't know whether that brings you anything?
No, we haven't done the... Okay, I have not done the calculation and the simulation yet. So that's something that we'll have to do, but we haven't done it yet. Scott?
You didn't mention anything about transit, right?
Well, there have been simulations done by one of the students from Eamon about transit. But personally, about transits with this kind of machines, I'm not very keen. Because, okay, they come for free. But frankly, in 2023, 2025, who cares about transiting planets on magnitude age 20 or 23? You cannot do any follow-up on them. I think it would, okay, I'm not convinced, even if it is for free, I'm not convinced about the science case. But if anybody wants to do it, that's perfectly fine with me, no problem. The only thing that I'm sure is that I will not work on it. Sorry.
I had a second question though. Have you thought about doing much higher cadence multi-band spectrometry? Because, I mean, you're not getting a huge number of planets, but it might be really interesting to try to distinguish between, like, how many have like sources by measuring color effects or contamination effects.
Okay, so right now it's every 12 hours that we will take this color information. But for example, if you want to go with the Viz, you can't because of the data rates. The Viz camera is much bigger, so we cannot take more than every 12 hours.
But you could do like H and Y.
H and Y, well, yeah, we could. But yeah, we could switch between 2 infrared, yes. But with the Viz, no. Plugging in the Viz every 12 hours is the max we can do. Well, the problem is that the cosmologists will not let us do this with their toys. Ask a cosmologist, oh, let's do this, maybe there is a risk for your satellite. I don't think a cosmologist will let us do it. And ESA certainly not. Sean?
So take your comment on that is that if you go more into some, does that just bring the batteries?
The thing is that it's ESA and the industrial who tell us you can work between -watts and +31. So basically this, because at the beginning it was from -1 +5, so we basically had to beg them for more. And but this number, it's not us, it's them. So it has been discussed with industry. So we'll see with the final version of the satellite, because you still have stuff that is being fine-tuned. So we'll see what will be the final number. But for sure, it will not be like W first. We'll not be able to do 70 days in a row. Yes?
What about onboard data reduction?
Uh,
I mean, particularly when it comes to visual ones, you have a much bigger area,
Yeah.
and you could try to reduce the data you actually have to bring down.
So for example, the problem is that we are not allowed to put any constraint on the onboard calculations. For example, the exposure time is fixed by the cosmologist. I think, because of course what you would say is that, oh, let's we don't know the image. You say, oh, there is a microlensing event here, so let's take just the window around it. That's what basically would make sense. But today there is no such facility. Possibly. So we're already struggling to be able to be finally validated. If we start to have this kind of requirement, they're going to shoot us.
Yeah. Nevertheless, it's software.
It's software.
Yeah.
Yeah.
This is something that can be changed later.
I would say let's get selected first, and once we are once we are on board officially, then we might. By the way, it would be nice if we could just take small. But I know, I agree with you. Yeah.